Good afternoon, class. Chapter 5, Integrals, 5.4 The Substitution Rule. So we covered the fundamental theorem of calculus, and we're going to move on to the substitution rule. And as always, basic integration formulas and the FTCs. The derivative of the integral is the function itself, evaluated at this upper variable. The definite integral of f of x dx from a to b, any antiderivative evaluated at the end points, capital F of b minus capital F of a would be the answer. And now here's the substitution method. F of g of x times g prime of x dx, where g of x is the u substitution, and this becomes du. And we're going to go over that. And in short, integration by substitution is the reverse process of the chain rule. So we remember the composite function, capital F of g of x. If we want to differentiate that, we get capital F prime of g of x times the derivative of the inside by the chain rule, which is g prime of x. And if we take capital F prime to be the lowercase f, as it is the case in the case of integration, lowercase f of g of x times g prime of x. Let u be g of x. Du dx is g prime of x, or du is g prime of x dx. And so we can write the following. The integral of f of u du is capital F of u plus c, or capital F of g of x plus c. So we differentiate it, and now that's the proof that we can go back to capital F of g of x. So over any interval for which u is g of x is continuously differentiable and f is continuous on the range of this function, the following relationship holds. The integral of f of g of x, g prime of x dx, where g of x is defined as u, g prime of x times dx is du, because du dx is g prime of x. Let me write that. Du dx is g prime of x. And that's how we arrive at du. Then the integral of f of u du, therefore, is capital of f of u plus c, where u is g of x. So that's the reverse process of the chain rule. So here's the tip. We want to look for a function u equals g of x anywhere in the integrand, such that its derivative du, or g prime of x multiplied by dx, is also. Generally speaking, when we have polynomials, this is a polynomial of degree 1, it's a polynomial of degree 2 being raised to the power of 3, in essence, polynomial of degree 6. The more complicated polynomial normally is the choice of u. So if we choose x squared plus 5 to be u, then du dx is 2x and du is 2x dx. To make sure we understand what we are doing, I'm going to move the 2x next to dx. Just going to move it. So we can clearly see this is u cubed and this is du. And we use the power rule, 1/4 u to the power of 4 plus a constant, and we replace the u with x squared plus 5. And as always, we can differentiate the result to check. And if we do so, we get this piece without the dx. Again, we are dealing with a bunch of polynomials. The more complicated one is x cubed plus 1. And we notice the derivative of that is 3x squared. We are going to move the 3x squared next to dx and use the substitution. Let u be x cubed plus 1. Therefore, du becomes 3x squared dx. So this becomes the integral of u to the power of 10 du using the power rule, 1 over 11 u to the power of 11 and a constant. We replace the u. So reversing the substitution, we are done. As always, we can differentiate the final result and it will give us the integrand without the dx. Again, we are dealing with a couple of polynomials. This one is more complicated than this one. So let's choose this one as a u. Clearly, the derivative is 2x plus 3. Therefore, du becomes 2x plus 3 times dx. So 9 remains. You can keep it in or outside. The integral sign makes no difference. This is u, 2x plus 3 times dx is du. And again, the power rule, 9 halves u squared plus the constant. Replace the u. And we are done. As always, differentiation will prove we have it right. Let's move on to a different type of function. This is a fractional function. This is a rational function. Anytime you have any of those, the very first step is, can I simplify it? Remember, a fraction must always be put into its lowest term. If we can, we must do that. If we cannot, normally the choice of u is the denominator. So for this one, if you choose u to be 5 plus e to the power of t, clearly du is e to the power of t dt. To make sure we understand what we are doing, I'm going to put the dt next to e to the power of t. It makes no difference. So we can clearly see that this statement is the integral of du over u. And as you know, this gives us a natural log. And you replace the u, reverse the substitution. This is the final answer. The only thing I want to add, this expression is always positive because, as you know, e to the power of t, the range is 0 to infinity. So 5 plus e to the power of t is larger than or equal to 5. You could change it to a parenthesis. Part B, you're going to ask yourself, can I simplify it? And that means, can I factor the denominator? So this can't be factored out, and I'm going to remind you of the following. If we have ax squared plus bx plus c, we are looking at this one. In this case, a is 1, b is 2, c is negative 1, b squared minus 4ac is called the discriminant. And when you evaluate that, the expression can only be factored if it's a perfect square. And when you evaluate that, you get 2 squared minus 4 times 1 times -1. 4 plus 4 is 8. And it can't be factored. Because 8 is not a perfect square. So what do? We just continue with the way it's given. Since we can't simplify, we let u be the denominator, which is x squared plus 2x minus 1. If we differentiate this, we get 2x plus 2. So it's 2 times x plus 1. And therefore, du is 2 times x plus 1 dx. 2 times x plus 1 dx. So with that being the case, let's put the dx at top. Notice number 2 is missing. So I'm going to show you an easy way. In many texts, they solve for dx, and I will look at that methodology, but to me, the easiest way, anytime we need a number, we just throw in the number here. And we can only do that with numbers. And then with its reciprocal, we undo it because their product must be 1. So again, number 2 is missing here. When you compare, you can throw in number 2, and then it's reciprocal. Because their product is 1, this is acceptable. And now you're looking at 1/2 the integral of du over u. Which is 1/2 natural log of u, and replace plus a constant and replace the u. That's the final answer. And by the way, this expression could be positive, could be negative. Therefore, we must keep the absolute value, whereas here we could have lost it. It's always positive. Now, on the same page, I want you to see the following and compare this to A. It's the reciprocal of A. And I want you to notice you do not need to use substitution. All you have to do, make up 2 fractions. This is one of them, 5 e to the power of -t. This is another one, which is simply 1. And as you know, we can divide by -1. In this case, becomes -5 e to the power of -t plus t and a constant. That's the final answer. Again, no need for a substitution. Be careful. Let's see what happens when we are dealing with exponential formats. Generally speaking, the choice of u is the exponent. So in this case, if we let u be x to the power of 5, du is 5x to the power of 4 dx. So I'm going to move this next to dx so it becomes clear that we have e to the power of u, and this whole statement here is simply du. And now the answer is simply e to the power of u and a constant, where u is x to the power of 5. As always, If we differentiate, we get this statement back without the dx. Part B is similar in that we're dealing with the exponential. So let's choose the exponent as u again, and this time the derivative of u equals x to the power of 5 minus 2 happen to be the same, 5x to the power of 4, therefore du is 5x to the power of 4 dx. So let us move x to the power of 4 next to dx, and we notice when we compare these two, number 5 is missing. And again, we can only do that to numbers. So if I plug in 5, then I need its reciprocal 1/5 so that their product is 1 and this is acceptable. Let's say you need 2/3, then you put 3/2 out here, they're reciprocal. And so what you're looking at is 1/5 of the integral of e to the power of u du, which is simply put 1/5 e to the power of u and a constant. Replace the u with x to the power of 5 and minus 2, and we are done. Needless to say, if you differentiate this, you get this expression without the dx. Again, I'm going to repeat. Number 5 was missing. I put in number 5 and then it's reciprocal. Many times they solve for dx. And in this example, I'm going to do it both ways because it's easy enough, really doesn't make much of a difference. Otherwise, the method that I went over is faster. So to integrate this, we let 3x plus 7 to be u. Therefore, du becomes 3 times dx. In this example, I'm going to do both ways. I'm going to solve for dx, and it becomes du divided by 3. And so what we have here is the square root of u, and instead of dx, du divided by 3. Square root of u, or u to the power of 1/2 du, and then divided by 3. Let's pull the 1/3 out. It's the same thing. I hope you see these two are the same expressions, but we put them in this format for the sake of the next step, which is integration using the power. Before we move on, let me show you again, and let me remind you of my method, which was simply put, if I look at this one, I notice number 3 is missing, right? 3 dx. So I just throw in number 3 and I undo it by putting 1/3 out. So I put the 3 in, 1/3 out, their product is 1. And now this is square root of u, or simply u to the power of 1/2, and this is du. And the 1/3 remains. So I hope you see they are identical. I believe this is easier, especially when this gets even more complicated. Now, this is an easy integration, 1/1/2 plus 1 u to the power of 1/2 plus 1 and a constant. The 1/3 doesn't go away, it's still there. This becomes 3/2. The reciprocal of that is 2/3. We multiply it by 1/3, and it gives us 2/9 u to the power of 3/2, and u is replaced by 3x plus 7. Again, I want you to see these questions side by side because both of them involve ln x, and anytime we have ln x, that is normally the choice of u. So let u be ln x. So the derivative is 1 over x, therefore du is 1 over x dx, and we can represent it in this format or in this format. And I want you to see both formats. And when you come across each one, it's easy to deal with. Now, you can go to the next step and start integrating, but I rather rewrite this in a format that it becomes absolutely clear what we are dealing with. So we have ln x to the second power, and we have 1 over x dx. I'm going to separate them. So you can clearly see this is u squared, and this is du. So this is u squared, and this whole thing is du. Using the power rule, we get 1/3 u cubed plus a constant. Replace the u with ln x, and make sure you keep that inside the parentheses, because ln of x to the third is not equal to ln x cubed. Those are two different things. This, we can rewrite it as 3 ln x. So those are two different things. It is extremely important to distinguish between the two. So let me erase it. So with this part B, again, I'm going to separate them so it becomes clear what we are dealing with. We are dealing with 1 over ln x, that means 1 over u. And then I put it in this, instead of 1 over x dx, I put it in this format, dx over x. So you see this format or this format. They both mean the same thing. So we have 1 over u du. 1 over u du. As you know, the integral of 1 over x is ln x. So the integral of 1 over u is ln of absolute value of u and a constant. And replace the u. So you have ln of absolute value of ln x and a constant. And if you differentiate that, you will get this part, 1 over x ln x, without the dx. You get 1 over x ln x. What happens when we are dealing with sinusoidal functions, trigonometric functions in general? In this case, notice the argument has an exponent. Therefore, the argument is a choice of u. If I choose u to be x squared, du becomes 2x dx. So I'm going to rewrite this by moving x next to dx. And notice this one, 2 is missing. So I'm going to throw in 2, and then I will undo that by putting 1/2 in or outside. The integral sign makes no difference. So what we are dealing with is 1/2 sine of u du. The derivative of sine is cosine, but the integral of sine is negative cosine, and that's why we have minus 1/2 cosine u and a constant. Replace it with x squared. And as always, if you differentiate, you get this statement without the dx. In part B, the difference is that the exponent is unsigned. This is sine to the second power. That means sine x times sine x. When sine and cosine are together, any of those that has an exponent, that's a choice of you, because the derivative of sine is cosine. The derivative of cosine is negative sine. You have to adjust for the negative. So if you let u be sine, du is cosine x dx. So simply put, this is u squared and this is du. And now you can use the power rule. 1/3 u cubed plus c, and u is replaced with sine 1/3 sine cubed x plus c is the final answer. Let's see what happens when we are dealing with a definite integral. The integral of 1 to 2, 2x x squared minus 1 quantity cubed dx. From a to b, a is 1, the lower limit is 1, the upper limit is 2. And as you know, a definite integral results in a number. So there are two ways to do that. One is to return to the original variable. We let u or g of x to be x squared minus 1, the more complicated one. Du therefore becomes 2x dx. And so as you can see, if I put the 2x next to this, we are dealing with u cubed with the du. And I'm not going to put the limits for a simple reason. Those limits pertain to the variable x, not the variable u. And we're going to get back to that in a moment. But for now, this is 1/4 u to the power of 4. Again, we're not going to discuss the limits here. We go back to the original variable, namely, we're going to change the u to x squared minus 1. And now we can use the original limits. A is 1, the lower limit is 1, b is 2, the upper limit is 2. Now, let's plug in 2. 2 gives you 4 minus 1, 3. To the power of 4 is 81, and 1 gives you 0. So it's 1/4, 81 minus 0, or 81 over 4, you're done. You can always return to the original variable. The second method is to keep track of the change of variables in the limits of integration. Meaning, the lower limit, x or a equals 1, put it into this function and evaluate it. So if x equals a equals 1, you put it into this function, g of a, and as you can see, 1 squared minus 1 becomes 0. Now the upper limit, b, x equals b or 2, you put it into the same function, gives you 4 minus 1, which is 3. So 2 squared, 4 minus 1 is 3. And therefore, this becomes this with the limits of 0 to 3. So this is the original one. This is the substitution from 0 to 3 now, which is, of course, 1/4 u to the power of 4 from 0 to 3. If you plug in 3, 3 to the power of 4 is 81, 0 gives you 0, and obviously we get to the same answer. Normally, when you do the u substitution, if you use the new limits, it's easier. And so the tip is, if g prime of x is a continuous function on the closed interval of a to b, and f is continuous on the range of u or g of x, then the integral of a to b f of g of x g prime of x dx is the integral of g of a to g of b f of u du. I hope you realize this is g of a, this is g of b, where u or g of x is x squared minus 1, where a is 1 and b is 2. That's the concept. You have to memorize that, understand what we did here. Here's another example. Let's do the u substitution, and that means the more complicated function, in this case 25 minus x squared, is the choice of u. Du becomes minus 2x dx. And so I'm going to move the x next to dx, and we notice that minus 2 is missing. We can throw in minus 2, and then the reciprocal of that is negative 1/2. Again, the product of the two numbers, and we can again do it only with numbers, not variables. For example, if x is missing, you cannot throw in x, just the numbers. Notice their product is 1. So this is the negative 1/2, the integral of square root of u du, and we're not going to put the limits yet. We will look at it in a moment. But for now, this is the answer. And so u to the power of 1/2, because we want to go with the power rule. This part is 1/1/2 plus 1. U to the power of 1/2 plus 1. This remains unchanged. And 1/2 plus 1 is 3/2. And 1/3/2 is 2/3. When we multiply negative 1/2 and positive 2/3, we get negative 1/3. Product of these two numbers, negative 1/3. So we can go back to the original variable and replace the u with 25 minus x squared and use the original limits 3 and 4. Or over here, we have to figure out the new limits. So how do we figure it out? First, we plug in 3. If you plug in 3 here, what happens? We get 25 minus 3 squared, which is 9. And the lower limit becomes 16. If we plug in 4 here, we get 25 minus 16, and the upper limit becomes 9. Now we do the elementary algebra and we evaluate the function at the endpoints. So negative 1/3 times the brackets, 9 to the power of 3/2 minus 16 to the power of 3/2. This one is square root of 9 cubed, which is 3 cubed, which is 27. This is square root of 16 cubed, which is 4 cubed, which is 64. This is minus 37 times a negative 1/3 gives us positive 37/3. Positive 37/3. Let's do this one, and there are a couple of polynomials, x squared and 2x cubed minus 8. Clearly, this is a more complicated one, and that's the choice of u. As you know, the derivative is 6x squared, so du is 6x squared dx. I'm going to move the x squared next to dx again, so it becomes clear what we need over here. Number 6 is missing. Throw in number 6. And then it's reciprocal outside 1/6. Again, you can do that two numbers again. So what you're dealing with is 1/6, the integral of 0 to 2, 2x cubed minus 8 cubed, 6x squared dx. This is u cubed, and this is du. And we're going to discuss the limits. For now, we're not going to put the limits, but we're going to figure out the limits in a moment. And that means plug in 0 here. If you plug in 0, you get 2 times 0 and then minus 8. If you plug in 2, you get 2 times 2 cubed minus 8. 2 cubed is 8, times 2 is 16, minus 8 is 8. And so the lower limit is negative 8. The upper limit is positive 8. The integral of u cubed is 1/4 u to the power of 4. The 1/6 outside doesn't go away. Their product is 1/24 u to the power of 4, and evaluated from negative to positive 8. If I want to go back to the original variable, I can replace the u with 2x cubed minus 8, and the limits are the original limits of 0 to 2. However, it's easier to evaluate it here. I'm going to show you why. This is 1/24. We have 8 to the power of 4 minus negative 8 to the power of 4. As you know, when the exponent is even, it becomes positive. So 8 to the power of 4, negative 8 to the power of 4, you don't even have to know what they are. They are identical. They cancel each other, and that gives us 0. And times 1/24, it is still 0, and we are done. The rate of growth of a fish population was modeled by the equation g of t is 30,000 e to the power of negative 0.6 t over 1 plus 5 e to the power of negative 0.6 t quantity squared, where t is measured in years since 2000, and g of t in kilograms per year. If the biomass was 40,000 kilograms in the year 2000, what is the predicted biomass for the year 2020? Now, in this case, lowercase g of t represents the rate of growth, and that means the derivative function. And according to the net change theorem or the accumulated change theorem, the amount of increase in the population, in the biomass after the 20 years, is biomass, I would say, rather than a population, then it's the integral of g of t from 0 to 20. So plug in g of t. And to integrate this, we are going to use the u substitution by letting 1 plus 5 e to the power minus 0.6 t represent the choice of u. Now, first I want to show you the derivative, and I'm going to go over that quickly. If I want du dt, I hope you realize you have 5e to the power of minus 0.6 t, and then we're going to multiply it by negative 0.6. This is how we get du dt. And that becomes, if you multiply these two, minus 3 e to the power of minus 0.6 t, and therefore du is the same thing times dt. So I just wanted you to see how we arrive at it. So differentiation of an exponential, it's very simple. Remember, in the case of a differentiation, we multiply by the coefficient of t. In the case of integration, we divide. So let me continue. So how do we deal with this? Well, you have a couple of choices. You can put the 30,000 out and say, okay, over here, minus 3 is missing. I hope you realize dt is the same as being at home. So you can put minus 3 and divide by it. Or you may see that, okay, you want negative 3. This is the product of negative 3 and what number? negative 10,000. And so you throw out the negative 10,000 outside the integral sign just to make it easy to see what's going on, and you keep the negative 3. When you do that, then clearly your numerator is du and the denominator is u squared. So minus 10,000 du over u squared. Notice I've changed the limits, but they can no longer be 0 and 20. And I put question mark because we don't know it yet. We're going to get to that in a moment. As you know, this is u to the power of negative 2 du, and the integration is 1 over minus 2 plus 1 u to the power of minus 2 plus 1. And this whole thing is negative u to the power of negative 1. So we have minus 10,000 times minus u to the power of negative 1. As you can see, this negative means positive 10,000 divided by u, or 10,000 times u to the power of negative 1. I want to figure out those limits. So what do? We plug in 0 into this. If you plug in 0, again, let me show you and then I erase it. If I plug in 0 in here, I get 1 plus 5 to the power of 0, and that is 1 plus 5 equals 6, because e to the power of 0 is 1. If I plug in 20, then what do we get? We get 1 plus 5 e to the power of minus 0.6 times 20, which is 1 plus 5 e to the power of minus 0.6 times positive 20 is minus 12. And that's what we have here. So again, the lower limit becomes 6, the new lower limit, and the upper limit becomes 1 plus 5 e to the power of minus 12. Let's erase it. And it is easier to evaluate this as 10,000 over times 1 over u. The lower limit is 6, and the upper limit, let's put this into a calculator, and it becomes almost 1.00031. So this is 10,000 times 1 over, let's say 1 minus 1 over 6. And since they wanted with 1 decimal, they wanted with whole numbers, so 8333 kilograms. And this is the amount of increase. How much did we have in the first place? The amount of biomass was 40,000 kilograms. Let's add to it. And now we have the final answer, 48,333 kilograms. So this is the accumulated change or net change theorem. And I wanted to remind you that we've done a similar question without the substitution, and there was a second method. The second method is this. Instead of evaluating it from 0 to t, let's do an indefinite integral and find capital G of t, which becomes right here 10,000 over u plus a constant. 10,000 over u plus a constant. And now we replace the u, and here's the initial value G of 0. In other words, from here, we go here and write plus c. We replace the u, and then G of 0 is 40,000. Now, if you replace the t with 0 and evaluate this, you get 10,000 divided by 6 plus c is 40,000. You can get to c, and c becomes this number. Now, you want the population or biomass after 20 years, replace the t with 20. And you get to the same answer. The advantage of this, again, is that even if they ask what is the population or biomass after 30 years or 40 years or 50 years, all you have to do is replace this t instead of going through the process from A to Z. I'm going to evaluate these integrals, and again, on purpose, I have two of them because they're similar, so I want you to see the similarities and differences in both cases. It can be simplified. The answer is no. So therefore, the choice of u would be the denominator, which is 1 plus x squared. Du becomes 2x dx. And so the first one, simply put, becomes the integral of du over u, which is a natural log. And you replace the u. And the reason I got rid of the absolute value, because 1 plus x squared is always positive, so we get ln of 1 plus x squared plus a constant. This, in fact, is always larger than or equal to 1. Otherwise, you have to keep the absolute value. When we go to the second one and we rewrite it, now, see, they are similar, but this results in a natural log. This results in using the power rule, u to the power of -2. And we've done this many, many times. So 1 over -2 plus 1, u to the power of -2 plus 1. This is -1, 1 over that is minus, so minus u to the power of 1, or minus 1 over u. And so minus 1 over u becomes minus 1 over 1 plus x squared. Don't forget the constant. And now we are done. So they look very similar, but one ends up being a natural log, one ends up being a rational function, two different things. Again, remember, the very first step is simplification if you can. When you cannot, then you move on. The same thing here, we can't simplify. And some of you may see the answer, some of you may not, but I want to go through the process. You let u be the denominator, and du becomes simply 1 times dx, or simply dx. So the numerator is du and the denominator is u. And again, in essence, you are here, you end up with a natural log here, if you will, and you replace the u, and now you do keep the absolute value sign for a simple reason, because the expression x plus 3 can be positive, can be negative. You must keep the absolute values.